Okay. So this is Simone Giannecchini. I'm the director at GeoSolutions. I'll do the introduction, and then I will leave you with Alessandro, who is our lead DevOps. He will tell you a little bit more about what he's going to talk about in the upcoming slides. But I mean, the topic is hot, as you might imagine, and it's again, I mean, ability to run GeoServer clusters in Kubernetes. Obviously, this is going to be an introduction, because we could talk for hours about this topic, but our hope is to give enough material to get started. We might turn this webinar into actually a workshop as part of our professional training offers. Anyway, a little bit of the introduction on GeoSolutions. GeoSolutions is an Italian SME. I'm one of the founders. We founded the company in 2006, a while ago, and we now have an office in the US as well. Our US lead should have been here, Luis, today, but he had some family matters to attend, so he might be late in the game, so that's why I'm replacing him. What do? We are an open source company, meaning that we develop solutions based on a number of open source products for the geospatial world. If you're here, you already know about GeoServer, but we work with other products, mainly Mapstore, which is a WebGIS that we developed, and it's open source. GeoNode, which uses GeoServer in the backend and Mapstore in the front end, and GeoNetwork, which is a metadata server. Our offer comprehends everything you need to use those products professionally. So professional services, which we call enterprise support services, deployment subscriptions, where you actually pay a fee and we help you with running these products in production with your deployments. We build customized solutions using them, obviously. And we do also professional services. Can you see my screen correctly, Alessandro?
Yes, I can.
Okay. We have had so far more than 200 clients. Our main markets are Northern Europe and North America, but we have clients mostly all over the world. Also through, let's say, organizations like the World Bank, UNFO, etc. We have worked almost everywhere in the world. We've worked with private companies, many of them, but also with public administrations, with NGOs, and so on and so on. Obviously, what we do is orthogonal to many different fields. GIS is used everywhere, as you might imagine. We started in defense, but then we have been working almost in every field. Here we are mentioning some of the most important ones. We strongly support OSGeo, obviously. We work a lot with OGC because we value interoperability and standards, and we actively participate in interoperability experiments and pilots every year. And our US subsidiary is a member of the USGIF. We are around 30 people. We are a very horizontal company. Most of us are software engineers. There is a small sales and administration team that runs the company, but most of the people are technical people in GeoSolutions. Here you can see some of the core people, and you can see they have leading roles in the various open source products that I mentioned before. Since we're here, we are hiring. We have a number of positions open. So if you're interested, you can find a link in the presentation afterwards, so you can apply. It's through our LinkedIn page. And I would say back to you, Alessandro.
Okay, thanks, Simone. I'm about to share my screen. Can you see my screen?
Yes.
Okay, so thanks everyone for attending. As Simone said, I'm Alessandro Parma, DevOps engineer at GeoSolutions. Let's have a couple of words about GeoServer in general before we dive into Kubernetes and containers. So what is GeoServer? GeoServer is a geospatial enterprise gateway. It's an open source Java application. Its role is to publish, manage raster and vector data. It's compliant with many different standards, OGC standards like WCS, WFS, WMS, and so on, if you're familiar with them. GeoServer supports many different data sources as input and provides you with many different formats as outputs. You can publish in GeoServer shapefiles, database sources like PostGIS, Oracle, and so on. Also supports several different kind of raster data formats, GeoTIFF being the most popular one. As output, you will get WMS endpoints, WFS endpoints, and so on. They are all listed here, and with many different image formats as well. So now let's talk about Kubernetes. So what is Kubernetes in general before we dive into how you run GeoServer in Kubernetes? So it's an open source platform. It's meant to manage containerized workload and services. It was developed by Google based on their experience with Borg. Borg is a product, an internal product meant to run applications at scale used internally by Google. Kubernetes manages a cluster of nodes that you make available to it and is running the containerized applications for you. It will help you running the applications, scaling them, and with other things that we will see afterwards. Okay, so we talked very briefly about what Kubernetes is. It's meant to run containerized applications, but maybe you don't know what a container is. So let's talk about containers. So what is a container? It's a type of virtualization technology that happens at the operating system level. You may be familiar with other kind of virtualization technologies like virtual machines, for instance. This is somewhat similar, but somewhat different as well. So applications can run in an isolated way. So in isolated user spaces called containers. What does it mean? It means they will have their own file system, for instance. They will not be able to talk with each other natively unless you explicitly grant them the permission to do so. They implemented at the kernel level in the operating system, so at a very low level of the operating system. What are the differences between containers and VMs? So virtual machines, if you're familiar with the concept, each one of them is running as a virtual machine, as its own full operating system running. You can have, for instance, on the same server, you can have Linux virtual machines, Windows virtual machines next to each other. They will have their own full operating system. The hypervisor is abstracting and managing resources for them. So things like CPUs, RAM, and so on, storage, for instance. This is all abstracted by the hypervisor. The virtual machine doesn't know basically that it's running in a confined environment and sees the resources that you granted to it. While deploying with virtual machines, you typically have many applications running in the same virtual machine. That's the most common use case. And for what the application can tell, it's pretty much looks like a dedicated machine. It doesn't know that it's running in a virtual machine most of the times. And this is pretty much transparent to developers and operations people. So they're managed pretty much in the same way as bare metal machines. Containers, on the other hand, there are different kind of visualizations. You can have many containers running on the same machine, but you typically don't have many applications running in the same container. So you typically deploy one application per container. The operating system, the kernel specifically, provides isolation and security. So even though they're running in the same operating system, they cannot talk to each other, and this is enforced by the kernel. It's pretty different if you're familiar with virtual machines in terms of tools and skill sets and so on. So it has its own idiosyncrasies, its own ecosystem, and so on. You have to study it a little bit and learn about it a little bit before you get fluent with running containers. The application with containers is bundled with its dependencies. This is quite different from the virtual machines scenario. So on a virtual machine, you typically install all the dependencies first, and then finally the application that you want to run in the virtual machines. With containers, you create what's called an image with the whole user space that's needed for the application to run. So the dependencies are packaged with the container itself. And that concept is quite useful. For instance, a developer can run the same image of a container locally and in the cloud, and it's going to have the same exact dependencies, libraries, and so on. So it's much more reproducible and portable compared to virtual machines. This is a small picture depicting the two scenarios. On the right hand, we have virtual machines running on an hypervisor, each one with its own guest operating system. On the left side, you will see containerized applications running in the same operating system. In this case, they're running in Docker. So why is it relevant? Why should you care about it? Why can't you just keep using virtual machines? So for some scenarios, it doesn't make sense to switch to containers, but there are some pros. So it may be convenient to do so. With traditional deployments, which means bare metal machines, you don't have boundaries between application of each client, and it's not easy to reallocate resources. So then it came the need for virtual machines, where you can actually easily change the allocation of resources to each virtual machine to have better utilization of the hardware resources of the server, and they provide better isolation. So the application from a project, for instance, is fully isolated from the application of another project. What's the need for containers? Containers are pretty much decoupled from the underlying infrastructure. So as you said, they're very portable, and they come with the full list of dependencies in the container. So that's one of the great pros of using containers. Another advantage of using containers is the image creation. It's much faster to create a new image for a container compared to recreating an ISO image or another kind of image for a whole virtual machine, for instance. And this is a good fit for frequent deployment scenarios and CI/CDs. So the whole cycle of redeploying the updated application is much leaner and faster with containers. This is another key advantage, in my opinion, of using containers. Another point is the separation of concerns between devs and ops, which may be a pro or not, depending on how things are run in your company and how you view things. So now developers can they can concentrate on develop the application on their laptop, without caring about too much about deploying the application, because once the application is packaged in a new image, they can pass it over to the operation guys, and they will just spin up the updated version of the image. They don't need to know all the details of the application. They don't need to care about the requirements, Java version, and so on and so on. And as you said, it's much more consistent between environments. So this isolation from the underlying user space makes it easy to port containers from one environment to another. For instance, from dev to QA environment or QA to prod, it's much more linear. So we talked about containers, what they are, and some of the advantages of using containers compared to virtual machines or bare metal servers. Then we can talk about why Kubernetes. So as we said, Kubernetes takes care of managing your containerized applications. So as long as you have just one container running, which doesn't look much like a production deployment, you can easily do it by yourself. You can manage it by yourself, restart it, stop it, and so on. When you start having several containers running in your infrastructure, it becomes harder to manage them. And it's pretty much unfeasible from a practical standpoint to manage many containers in from the command line. So you need what's typically called an orchestrator, a helper basically to schedule containers, deploy them, and taking care of them. Kubernetes would, for instance, decide where to deploy your application. On a distributed system, for instance, it will find out, based on the resources available, what's a good candidate to run your application. It's going to scale the application for you, both manually and automatically if you want to, based on metrics like CPU usage and so on. It's going to restart your containers if they fail for some reason, and so on. It also comes with a set of abstractions like service discovery and load balancing, which you would have to implement yourself, and it's not an easy thing to do. What I mean by service discovery is a container is capable of talking with another container just by referencing it by the name. You don't really have to mess around with using IP addresses, know what's the current IP address of a given container and so on. You just reference the name of the service. And it's also going to do load balancing for you. So if you have multiple instances of an application running, Kubernetes is going to spread the load across all of the instances. You don't have to worry about it. You don't have to set up a proxy for it and so on. Also, storage orchestration. This is another nice abstraction of Kubernetes. You can attach several different kind of storages to your cluster. And from the developer and the sysadmin standpoint, it's going to be pretty much transparent. It's going to work with different kind of storages. It's going to manage rollouts and rollbacks for you to simplify the updating of the application and so on. And also self-healing of services, as we said, in case a container fails, for instance, it's going to restart it, and it's going to hide misfunctioning containers from the end users. Also, some other relevant things are configuration management and secrets. So you can store passwords in a safe way in a Kubernetes cluster, and also save configuration for an application in what's called config maps. This is a nice feature to have. It's going to allow you to update the configuration of your application without redeploying it entirely. Kubernetes is not the only orchestrator available out there. There are alternatives. Some popular ones are Docker Compose and Docker Swarm. If you've been working with Docker, you probably know both of them. So Docker Compose, how does it compare to Kubernetes? It's a very much a lower level tool and system. So Docker Compose allows you to deploy several containers as a whole, as a service, but not much besides that. So you don't have many of the features that I described to you before. And especially, it's not going to work in a distributed environment. So Docker Compose only cares about running containers on a single machine. Docker Swarm overcomes that. So Docker Swarm can work in a distributed environment. It's not as sophisticated, again, as Kubernetes, but it has quite a nice feature set, and it's easy to set up and maintain compared to Kubernetes. So I see this more, Docker Swarm, more of a tool for small to mid-size environments. Kubernetes probably more as a tool for mid-size to large-size deployments, like production deployments. Yeah. Another one would be Rancher. You may be familiar with it. It was quite a popular, and probably is today, quite a popular tool. It started before Kubernetes became popular in the field. And it used to have its own container engine called Kettle. Since Rancher 2, which was released a few years ago, it dropped the support for its own internal engine, Kettle, and it's now used to deploy and manage Kubernetes cluster. So it's not something that is competing with Kubernetes anymore. Now it's using Kubernetes at its core. Here you will find a list of resources for what I've been talking about, in case you want to dig a little deeper and find more information. Some of the key concepts for Kubernetes before we take a look at how GeoServer is deployed in Kubernetes. This is the global architecture of a Kubernetes cluster. So as I said, Kubernetes is going to manage a set of nodes. It's really meant to be used in a distributed environment. Its heritage comes from Borg, this tool developed by Google for large-scale deployments. So it's really meant to use for that. So you set up a set of nodes. You give Kubernetes control of these nodes, and we can divide the nodes in two groups: a control plane, which is what is basically the brain of Kubernetes, and a group of worker nodes, which are what's going to run your pods. So the worker nodes are basically container capable machines in the sense that they can run containers, they can run pods, and they connect back to the control plane, to the brain of Kubernetes. And Kubernetes is going to schedule containers across them. There are other components. If you want to dig deeper, there are other components in the control plane. For instance, we can identify components like the API server, scheduler, and controller managers. API server is the user-facing service, basically. It provides APIs to talk with Kubernetes and to understand what's going on, but also to instruct Kubernetes about what it should do. It has a scheduler, of course. It's deciding what should run and where. So on which node, for instance, and a set of controller managers. We will see what they are a bit more in depth in a minute, but they basically make sure that the current state of the application is what we asked for. Worker nodes are running this set of services, a container runtime like Docker, for instance, but it can be another one. This is abstracted and it works with other environments, with other running environments like Containerd. A proxy for intercommunication in and out of the pods that are running in the cluster, and a kubelet, which is a service that connects back to the brain of GeoServer, to the brain of Kubernetes, and is making sure that containers are running as they should in the pods. So we can take a closer look at the concept of a pod, which is, because it's quite an important one. It's a central concept in Kubernetes. It's basically a group of containers with a shared namespaces and file system volumes. So what does it mean? Shared namespaces means they can talk with each other just by referencing each other by the name. So I don't know if you had GeoServer and GeoWebCache in the same pod, which would not be typical, but it's just for an example. They would talk with each other, referencing each other as GeoWebCache and as GeoServer. They don't need to know the IP address and so on. And file system volumes. So containers in the same pod are running on the same node. They are co-located, they are tightly coupled, and they're also sharing the file system of the node. So in some cases, this is useful if you want to grant access to multiple containers to the same underlying files. An example of a pod running more than one container would be a content server serving container, like I don't know, a web proxy or something similar to that, along with a sidecar container that is updating the content of the web page. That would be an example. So pods can be scaled horizontally. So you can run multiple instances of the same applications, which are called replicas of the pod in your cluster. This is a small image depicting what I said before. The example of a web server and another container updating the content of a volume, of a shared volume in the same pod. Then we have controllers, as I said before. This is another resource in GeoServer. Controllers manage resources. There are many different kind of resources that you can define. We will look at some of them. And they're going to manage the replicas of the resources. So for instance, spinning up multiple replicas of a given pod, of a GeoServer pod, for instance. They will manage rollout of updates, checking the health states of the pods. So if they fail, they will take care of reinstantiating the pod, maybe in a different node if needed. That's the typical example. So you have a node failure. So one of your machines is not working properly. A controller will find out that it's not running properly. It's going to find out that your pod was running on that node, and it's going to reschedule it on a different node. And this is all done automatically for you. Here we have a few examples of resources that are managed by controllers, deployments, stateful sets, and daemon set. We will look at them in a second. Here we have an example of a resource definition. All your resources in Kubernetes are defined in manifests, which are files in YAML syntax. Here's a small example of a resource. This would be a job. The kind of resource is a job. And underneath it, you have a template filled up with all the details for this job. So the container image that should be running, the command for this job, and so on. We will see more examples of this in a second. Now that you have some familiarity with the concept of containers Kubernetes, you may want to start testing these things and start to learn about how they work and how you operate them. There are a few ways to get started. One of the most popular one is Minikube. So Minikube allows you to spin up a cluster locally on your machine. So as long as you have decent resources available in terms of RAM and CPU, you will be able to spin up a cluster on your laptop or your workstation. Minikube is compatible with Linux, Mac, and Windows, if I'm not mistaken. So it's an option available to most users. Another way would be relying on a cloud service. So all major cloud providers today offer Kubernetes as a managed service. It's very popular, so they all have their own offering of Kubernetes as a service. And it's typically paid by the hour. So you can easily spin up a cluster and start playing out. Just remember to spin it down when you're done, because otherwise you get billed, of course. Okay, what do you need to run GeoServer in Kubernetes? As we said, we want a container image for GeoServer. There are many options available on the Docker Hub. Docker Hub being the public central repositories for Docker images. GeoSolutions has its own implementation of the Docker image. There is a link to the Docker Hub repository where you can find it and pull it. And there's also a link to the sources over on GitHub that you can pull and tweak and maybe debug if you find a bug, or you can signal a bug to us by opening an issue, for instance. That would be nice. There is also a community Docker image for GeoServer, but it's a work in progress at the moment. It's not done. It's almost there, but it's not done yet. I highly suggest you use one of these two or others available in the hub, because most of the work is done already for you. It's based, our image is based on the Tomcat image, and it's built periodically by the Docker Hub. So it's updated periodically as new versions of GeoServer come out, as new nightly builds of GeoServer come out, and so on. It's ready to use even for production scenarios. You just need to change the web app should you need it in the container, and make sure that you map the relevant directories out of the container for persistent storage. Let's take a look at an example of a Kubernetes deployment of a GeoServer. So this is the real thing. This is probably what you've been waiting for. It's a typical deployment that we do for our customers. We can see that it's a back office slave setup. So it's a passive cluster. If you followed our previous webinars, you know what I'm talking about. It's a passive GeoServer cluster with the back office and slave instances. You can see our Kubernetes ingress at the top. A Kubernetes ingress is basically a reverse proxy for your services. Then we have 2 branches. So we like to keep things separate. Back office and slaves. We like to have 2 branches in our deployments. A dedicated service for the slaves. A service is what gives you basically load balancing. It's an endpoint that you can use in your applications, in your other applications running in the cluster to reach the GeoServer slave instances. And in green here, we have the real thing. So we have a stateful set or deployment. We like to use stateful sets for GeoServer with all the replicas in it. We will look at what a stateful set is in a second. Finally, below you can see all the volumes, secrets, and config maps. Config maps are these YAML files where you drop your configuration for the applications. In GeoServer, you would use them, for instance, for your context XML file for Apache Tomcat, where you store the database connection details. That's a configuration for GeoServer at runtime. Another example would be the master password. Then volumes. There are several kind of volumes that we define, and we have defined in our Docker images. Some of them are meant to be shared between GeoServer instances because many instances need to access them at the same time. Some of them are meant to be local, and I'll tell you more in a second. Finally, we have a database connection. In this case, PostgreSQL. Typically, you would use a service provided by a cloud provider for this. So I depicted it as an external service to our Kubernetes cluster. Yeah, so as I said, a passive cluster with a back office instance defined as a stateful set. We have dedicated resources for back office and slave. What do I mean by that? I have a dedicated service for the back office instance. I have a dedicated stateful set for my back office instance, and so on. Why you don't need to do this, you don't have to do this, but it's easier to deal with, to operate on a daily basis. You can have different specs in terms of hardware, for instance, between the back office and the slave, and you can have different endpoints and policies for your back office instance. For instance, you may decide at the ingress level to not expose the GeoServer web interface to the user, to the end users, and so on. Secrets, as I said, database connection details would be a good example of secret use in GeoServer, and the master password. If you don't know what the master password is the seed password that is used to decode all other encrypted information in the data directory. So if you look at your GeoServer configuration, the data directory, inside it you may have some secrets like database connection details, users, passwords, and so on. These are all encrypted. And if you know the master password, you can decrypt them. So that's why it's meant to be a secret stored, and it's meant to be stored in a secure way. Okay. Database connection details, host name, ports, numbers, and again, username and password. You would store them in secrets or config maps. So that they are not part of the core stateful set for GeoServer or of GeoServer, and each environment would typically have different config maps with different secrets in them. So the base stateful set would be the same, but in dev you would have a different connection details for the database compared to prod. Finally, volumes. So volumes is a Kubernetes concept that abstracts the underlying storage. It's managed in a quite an elegant way. This abstraction allows you to work with different kind of storages, like local storage, NFS storage, or object storage, and so on, in a pretty much transparent way, from the point of view of the application that you're deploying, from the point of view of your developer, and so on. You can have different storage classes defined in your Kubernetes. When you ask your administrator to set up a volume for you, so some piece of storage for you, you can choose then the different storage class that you need for that specific thing, for the thing that you want to store in it. I think I have details below, so let me just, yeah. Just have a stateful set. Let's take a closer look. Stateful set contains things like the pod definition. So what containers are defined, are meant to run in my stateful set. The number of replicas, so how many of that containers should be run, of that pod, sorry, should be run. Health checks. You can define probes in your stateful set, and Kubernetes is going to check these probes. It's going to run these probes against your pod to know the health status of your pod. If a probe fails, the pod will be either excluded by the load balancing of the services temporarily or entirely restarted. It also contains references to volumes. So that's where you would say GeoServer needs access to a data-day volume, cache tile volume, and so on. Config maps, as we said, database connections, and so on. Same for secrets. It also contains environment variables. So it's quite important. As part of your pod definition, you define your environment variables, like the Java ops, for instance. If you followed previous webinars, you know what I'm talking about. They define some parameters of the Java virtual machine that is running GeoServer, and they set some properties to configure your GeoServer. Here's an example of a stateful definition specific for a GeoServer pod. You can see it's a YAML file, as we said. You can see the kind is stateful set. Then we have some metadata. So the name of my stateful set would be GeoServer slave. A selector for the controllers to identify the service, and the number of replicas. So in this case, I'm running 3 copies of my GeoServer slave pod. And finally, the spec, what's called the spec for the pod, with all of the details. In this example, we have our container called, again, GeoServer slave, the Docker image that is used to spin up this container, Then we have resources. You can enforce resource limits in Kubernetes. So here we're saying this pod is not meant to use more than 6 GB of RAM, for instance. And you can request resources to Kubernetes. This information is used by the scheduler. So you're saying this pod should be using, while it's running, more or less 7 GB of RAM, and it should be using 4 CPU cores. You should be reserving these resources for me, for my pod. This is helpful for the scheduler, to decide where to deploy this pod. So it's not going to deploy the pod on a node with less than 7 GB of RAM, for instance, or less than 4 CPU cores available. But these are not enforced. What's enforced is the memory limits. So the limits, in this case, a limit of 6 GB. Actually, there's an error in this stateful set definition, because this is lower than the requested amount. But anyway, should the pod reach 6 GB of RAM utilization, it's going to be killed by Kubernetes and restarted, rescheduled. Another maybe interesting thing in this pod definition in our spec is an init container. This is run before GeoServer is started. So it's another container that is started before GeoServer. We use this for different kind of purposes, maybe to prime some directories, to create them in case they're available yet in volumes and so on. Then, as I said, this is the continuation of the previous file, of the file that we were looking at in the previous slide. The environment variables, namely Java ops, are defined in here. Here's just an extract where we define our gweb cache dir location and the config dir location. The ports that should be exposed by our pod, and the volumes. The list would be quite long. Here we define our data directory volume and our master password volume. So it's linked as a secret into the pod. Logs, in this example, we are saving logs on the host, so on the node that is running the pod at this specific location. So we're not using volumes to store these logs and audit files. We're using the local storage of the node, which is ephemeral. It may, in case your pod gets rescheduled, you're going to lose it. But we're not too much concerned about it, so we save them locally for reasons that I will explain in a second. And finally, our server XML file for Apache Tomcat, we configure that as a config map so that you can tweak it at runtime without the need to rebuild the entire application, the entire Docker image, just to tweak the server XML file. Okay. Shared volumes, in our example above, we were using shared volumes for the GeoServer data directory and the geospatial data. So the data directory needs to be accessible by more than one GeoServer instance. Typically, all of your slave instances are going to need to access the configuration directory, the data directory at runtime. So that's why you would use a file share for it. This makes sure that it's reachable from all of the nodes of the Kubernetes cluster. Another example would be geospatial data. So your raster data, typically, you don't want to replicate the same files on all the nodes of a Kubernetes cluster. You just put them in a file share and they're available to all the containers. And finally, the cache tiles, you want to store them not always, but most times on a shared, some kind of shared storage. Could be an NFS, could be an object storage, so that a tile that has been cached by GeoServer, it's available to all of the nodes in the cluster. They don't have to recreate their own cache all the time. Local storage, as we were saying a moment ago, we use it typically for log files and audit files. Why? Because we don't really care too much about them. We don't keep the logs and audit files on the node for a long time. As they are produced over time, we ship them over to external storage for later analysis as needed. So we archive them off the node. So we don't care if we lose them for some reason. Say a pod dies and gets restarted, rescheduled by the controller. It may be deployed on another node where the previous log files and audit files are not available anymore, but that's not a problem for us. Another reason is local storage is typically fast in terms of latency. And GeoServer is quite verbose as it logs events to log files. So we don't want to be waiting on IO writing to the files. We want fast storage for logs. Here, there's a few examples of volumes, config maps, and secrets definitions in manifests, in YAML manifests. On the top left, we have a persistent volume claim. Technically, it's not exactly the definition of a volume. It's a definition of a claim of a volume. But you can see how it works. So again, the kind of resource at the top, then you have your spec, defining all the aspects of the resources, of the resource. You can have multiple access modes for your volumes. Here we're asking for a volume with access mode read, write, many. So it's meant to be shared storage. It's meant to be writable by multiple instances at the same time. Kubernetes is smart and is going to be used the appropriate kind of storage for it. On the right, the server XML file I was talking a moment ago. You can see the kind here is config map. So we're defining a config map with a data section containing the name of the file and the full payload of the file, so the content of the file. And finally, a secret, an example of a secret. I'm not going to show you all of it because it contains the password for some database. Again, kind secret, and in the data field, you have the name of the file and the whole encrypted string containing the password. Actually, the connection pool definition containing itself the password. Other kind of resources that you can define and are quite useful in GeoServer, in Kubernetes, besides the ones that we talked about, stateful sets, services, ingresses, pods, and so on. You can define jobs and daemon sets to run tasks periodically, should you want to. Jobs are indicated to run one-off tasks or tasks periodically, as I said. Daemon sets are basically pods that are running on each node of the cluster. So if you want to have a container running on each one of the nodes of your Kubernetes cluster, you can use a daemon set for that. We use them, for instance, to clean up the logs and the audit files of GeoServer. As I was saying, we store them locally on the node. We definitely don't want to fill up the storage of the local machine with logs and audit files. So we make sure we rotate them, and we use a daemon set for that. So this spec is going to be applied on each node. This is running, for instance, a log rotate container on each one of the nodes of the cluster, and cleaning them up. Finally, scaling is one of the features available to you. It's one of the things that Kubernetes does for you. You can easily scale a stateful set like the GeoServer stateful set that we have defined from the command line, should you need to. Using kubectl, it's just a matter of specifying the name of the stateful set and the number of replicas, and the controllers will take care of spinning up the other replicas of the pods in the cluster. But you can also use what's called a horizontal pod autoscaler, which does scaling in an automated way for you. And you can define how and why it should trigger. A typical example is based on metrics like CPU usage. So if the CPU usage gets above a certain level, Kubernetes is going to spin up more replicas of the pod for you to lower the load and to meet the target performance. Besides these two mechanisms, there is also a node scaling feature. It's available on some cloud providers, and you can instruct Kubernetes to talk with the services of the provider and shrink or enlarge the whole Kubernetes cluster based on some metrics. So, for instance, if Kubernetes is not able to schedule a new pod because it doesn't have the resources available on your nodes, it can spin up a new node, attach it to the cluster, and then deploy the container. And when the resource usage comes down later on, it's going to shrink them. So on AWS, it would use auto-scaling groups for EC2 instances, if I'm not mistaken, to do this kind of to perform this kind of activity for you in a transparent way. It's pretty nice. So you don't have to overbook your instances. You don't have to buy too many nodes in advance. So yeah, we're pretty much coming to the end of the webinar. Just a few final words, conclusions. What are the takeaways for the webinar? Containers are changing the way we deploy the applications. You can run GeoServer in Kubernetes, definitely. There are Docker images available for you on the hub. Some of them are developed by GeoSolutions, and I put the link in the slides. Kubernetes deployment requires you to define many resources, as you saw, like stateful sets, volumes, secrets, and so on. And you need to choose the appropriate storage class for each volume. So you need to be careful on the kind of storage that you use for to store your data there, for instance, compared to the audit files and others. Now I want to take a look at the Q&A panel in Zoom to see if you have some questions. I'll try to address them. One of them is why stateful sets and not a deployment? It would work. So they're kind of similar in terms of a resource in GeoServer, in Kubernetes. They're quite similar to one another. You use them to define your pods. A stateful set, as kind of the name implies, is really meant to be used to for applications that have a state. And we like it better compared to deployment because it's more predictable. When your pods are spinning up, for instance, you will clearly see in the name of the pods, GeoServer slave 0, 1, 2, 3, 4. When you use deployments, they're going to get a pretty much pseudo-random names, and we don't like to deal with them. So it's easier and more predictable. If we want to look at the log files, for instance, in for an incident, say a GeoServer died, you know that the slave number 2 died. You look at the logs directory, you will immediately find the name of the log for that instance. So it's just basically convenience. It doesn't really have to be a stateful set. It could be a deployment. Is there a specific reason why you haven't stored the GeoServer state in a database using JDBC config plugins? We don't use it that much. You could do that. So in the example that I showed you our GeoServer cluster was a passive cluster where the data so the data directory was stored in a volume. You can choose to store it in a database should you want to. We find it works okay, but if we find storing the configuration on a volume is more to be more reliable. So that's why we like it better. Does GeoSolutions have a Helm chart to deploy GeoServer? Yes, we do. We developed our own Helm chart for GeoServer. We're probably going to cover that in another webinar or in a workshop or something. We haven't published our Helm chart for GeoServer yet. If we do so, we will make it available in a blog post. So it's going to be available for you to take a look at. Is it possible to show deployments or how it was done? We were using stateful sets, so not really, not at this point. How do you synchronize GeoServer catalog between master and slaves? That's an interesting question. In the example we had, the data is stored in a volume, but you could also choose to store the data there in the Docker image itself. So if you store the data directory in the Docker image, it's just a matter of rolling out the image of the master or the back office instance to the slaves. So you're updating the slave image with the one that is used by the master. If you use volumes, you'll have to rely on some other external entity to do that for you, to synchronize the catalog. For instance, a CI/CD tool like Jenkins could do that for you. You can imagine having a pipeline to release the configuration from the master to the slave, and that pipeline also takes care of synchronizing the data directory from the master to the slave. Okay, let's see other questions. Do you deploy GeoServer also on private servers, and how do you handle database there? Definitely, yes, we do. We have done it for some of our customers. At that point, we manage the database ourselves. We deploy it in the cluster usually. There are some recipes available out there. For small deployments, you would just have another stateful set for, say, PostgreSQL, configured the way you want it. For more medium to large scale deployments, you could start thinking about using a Postgres Operator, for instance, which is a more advanced concept in Kubernetes. It's kind of an entity that allows you to manage the application. Basically, it's in charge of managing the application for you. Should you have a PostgreSQL cluster, for instance, the operator would take care of spinning up the cluster for you, adding replicas to it, and restarting the pods again should they fail, and so on. So in a more complex scenario, in a bigger scenario, I would use an operator. There are a couple available. One from Zalando, a nice PostgreSQL operator. There is another option from Crunchy. So if you Google it, you will find the operators from those two companies. How does Kubernetes compare to AWS ECS? I'm not an expert on AWS. My understanding is AWS ECS is managing the container. So the container as is. You don't have all the extra features available and exposed to you, like services, like volumes, I don't know, rollout features available in Kubernetes. So it's much more a simplified version. It's not as feature rich as a Kubernetes cluster. I've never used it myself though, so please keep that in mind. I've never used ECS myself. Different GeoServer instances share and edit the same data there. Could this bring sync problems? Yes, definitely. You should never do that. Not in the cluster type that I described above. So the back office instance in the cluster that I depicted is the instance that is dedicated to manage the GeoServer configuration. All the access to the GeoServer UI and changes to the configuration, like publishing layers, stores, editing styles, and so on, they should happen only on the master instance, so on the back office instance, not on the slaves. That would bring a sync problems indeed. That's a good question. Can Kubernetes detect leaks and automatically restart your server? You can enforce limits for your pods, so you can ask Kubernetes to restart your pod when they use more than a given amount of RAM. That's defined in the spec of the pod for your stateful set or deployment. You can also define probes that are going to check the health status of your service. If one of these probe fails, then you can decide what action to take. It could restart your pod or take it out of the load balancing temporarily, and so on. So you could also use that feature of Kubernetes. How do slaves know the data on the volume has been updated? Do you need to restart the slave? Yes, in the cluster that I depicted, they're definitely not aware that the data here has been changed. That's up to you to trigger a reload or a restart of the slaves. So you make changes in the back office instance. When you're happy, you trigger your pipeline and that's taking care of restarting the slave instances and also synchronizing the data directories as needed, as I was saying before. Hi, Vanessa. Why do you create a back office and a slave service? That's something we discussed in a previous webinar, but also touched probably while I was replying other questions. So the back office instance is meant to be used by the GeoServer administrators. It's not end user facing. It's meant to be used by administrator to make changes to the configuration. The slave instances instead, they're meant to be accessed by the end users. Let's see more questions. Besides ease of deployment, is there any advantage of having data there replicated instead of having it on a shared volume? Not really. Probably if you have a very large cluster of GeoServer instances with many instances, you can have a benefit of having a replicated data there in terms of startup times. So if you restart the whole GeoServer cluster, all of the instances at the same time, they would all try to read from the same shared volume at the same time. It's typically not an issue, but if you have a very large cluster, you may end up with slow startup times due to that. So many pods trying to access the same shared volume at the same time. And if you're not sharing the data there and you're deploying in Kubernetes, I suggest you evaluate the option to burn the data directory directly in the Docker image for the slaves. So in that scenario, the pipeline that is in charge of taking your configuration from the back office to the slaves is also going to produce a new Docker image with the updated data dir, GeoServer data dir in it, and roll out that image to the slaves. So then you have a data directory. Each container has its own data directory in its own file system, and it's also kind of versioned. If you see, so you have a Docker image for that specific version of the data directory. So that's also a nice advantage in that scenario. So we're asked if we're going to share the slides deck. Yes, they're going to be available after the webinar, probably not today, maybe tomorrow. They will be available definitely. As well as the recording of this webinar, that will be available too. Bare metal usage or versus Kubernetes usage, how do you decide which one to use? That's a very broad question. Bare metal, by bare metal, I see that you mean, I guess you mean you're not using containers at all. So if you go back to the beginning of the webinar, I talked a bit about the advantages of using containers in terms of isolation, speed of development cycle, and so on. So that's a good reason to use an orchestrator like Kubernetes or others to run your containers. For us, that at GeoSolutions who manage many GeoServer clusters for many different customers, it also gives us a nice abstraction from the underlying infrastructure. So we don't really care if we're using containers. We don't really care about the distribution that you're using, the Linux distribution that you're using, if you're using a bare metal server or a virtual machine, because we have our own application package with dependencies as a Docker image ready to be deployed, and it's going to look the same in all environments. So that's also a nice plus. In terms of performance, I don't really see a performance hit in using containers. So I would advise you to opt for containers if you can, especially compared to bare metal. So definitely, yeah. Another question, how would you handle synchronizing the data directory for high frequency time varying data sets? That's probably not a Kubernetes related question. And it's something that we addressed in previous webinars. So you've oftentimes, I'm just going to briefly reply, and then you can refer to previous webinars where we talked about how to handle configuration changes and so on. So you would typically don't need to change the data directory as your data changes over time. So if in most of the times, like 95% of the times, if you're ingesting data in GeoServer and you're also publishing new layers, you're publishing the new data as new layers, you're probably doing it wrong. And you should rethink how you're publishing data in GeoServer. So that probably shouldn't be a data directory change. That's how I would handle it. Another option, if your use case is to really have frequent configuration changes in GeoServer, then you can probably set up an active cluster instead of the passive cluster that I showed you. Again, please check the other webinars. We have some insights for you. Sergio, based on ease of deployment, is there any advantage of having data tier replicated? I think I've already answered this one. Is there an official GeoServer image? Not yet. We've been working on it. It's almost ready. It's going to come out soon. So it's going to be advertised as it becomes available. In the meantime, I suggest you use one of the other ones. Ours, in my opinion, it's of course a pretty good one, a good starting point. Is there an affinity setting in Kubernetes in load balancer to bind the users request to a specific? I think you can do that at the ingress level. I'm not 100% sure. Okay, I think we pretty much run out of questions. Let me take a look. I'm deploying a GeoServer on a virtual machine with external volume, putting the data tier in the volume. How do you manage data in this scenario? Typically a shared volume, as we said, a shared volume which is reachable from all the pods running on all the nodes of your cluster. So unless you have very strict requirements in terms of latency for data access, that's usually the way to go. Using an external volume, especially if you're maybe that's not your use case, but if you're using Kubernetes from a cloud provider, that also gives you access to some nice features, extra features like ease of taking backups, for instance. And that would definitely be good if you don't want to lose the data in your storage. So yes, I would use a shared volume in Kubernetes. All right, I think I've answered all the questions. So I'm gonna wrap this up. You will get an update with the slides and a link to the recording. If you don't, just head over to our blog post and you will find an updated version of the blog post with the links to the slides deck and the recording of the webinar. I thank you all very much for attending, and I will see you in upcoming webinars. Bye-bye.
No, perché tu la versione vecchia non si può vedere,